right. Hello, everyone, and welcome to the Marshall W. Allworth Planetarium. My name is Jessica. I am the director and will be your tour guide to the Northern Lights tonight. You've also met Brayden, one of our students who's helping out with the show tonight. But we're very excited for this show. It's always a popular one, especially this time of year. We'll talk about all sorts of good stuff when it comes to the Northern Lights, what they are, what causes them, and we'll give you some tips and tricks to try and see them for yourself as well. Now, if at any time during the show you need to leave, you are absolutely welcome to do so. You'll just exit through this front door up here, the same one you came in. If you need it, bathrooms are down back in the atrium of the building where you walked in by the telescope. And if you have any questions throughout the show, feel free to just ask. I can't always see hands from the back, so you're welcome to just ask your question out loud. But if you are not comfortable doing that, you can always come talk to me after the show as well. That's it for now, so I'm gonna head to the back and we'll get started. Okay. Now, as I said, our show tonight is The Mystery of the Northern Lights, which is, of course, this beautiful, glowing, dancing curtain of lights that we sometimes see up in the night sky. Now, before we get into the science of it, I like to also give a little bit of kind of cultural background to the aurora as well, since this is something that people on Earth have been seeing and experiencing since as long as there have been people on Earth. So the other term for the northern lights is the aurora borealis. And that name actually has its roots in Greek and Roman mythologies. So the word aurora is derived from the name of the Roman goddess of the dawn. So she traveled from east to west, announcing the coming of the sun. And then the term borealis stems from the Greek word boreas, which means wind. So the aurora borealis is like the northern winds that bring the light, which kind of makes sense. It's a good description for what you're seeing here in the sky. But there are some other interpretations as well that I really like. Occasionally, you could see auroras in China during, long in the past. And they were very rare occurrences. So when they did happen, they were seen as great battles between the good and evil dragons. And whichever one won determined what, the foreseeable future was going to be like. To the Inuits, the aurora was kind of the spirits of their deceased, their loved ones, who were playing games up in the sky. And as the lights danced around, that's them running around in the sky playing games. I really like that one. I think that one's sweet. But I think my favorite comes from Finnish folklore, and it's the tale of the firefox. There's actually a really great little animated short that talks about this tale of the firefox. So I figured we could take a few minutes and watch that. You can learn a little bit more about the Finnish firefox. All right. So there you have it, the finished tale of the Firefox. If you're interested in watching this again for yourself, it's easy to find online. It's Foxfires, an animated short, and it's fantastic. I love it. I always feel so sad for the little fox when he's trying to first get up in the sky. Anyway, so now that we've looked at a little bit of kind of cultural history and significance with the aurora, let's get into what's actually going on here. When we see these dancing curtains of light, what are we actually looking at? Well, to get that view, we're going to have to hop up into space and take a look at the Earth first. So, looking at the Earth, we see that the aurora is actually a ring of lights centered around the northern part of the Earth. It's not directly around the North Pole, and I'll talk about why in a little bit. But these dancing curtains are actually what we call an auroral ring around, near around the North Pole. But if we venture on down towards the South Pole, we will see a very similar occurrence down in the South Pole. And this is the aurora australis. And it's the same thing. We have an auroral ring around, kind of near the South Pole. And who can see the aurora and how intense it is depends on this ring. It depends on how big it is and how bright it is. And that's what's going to determine who can see it and the intensity of it. But then that comes back to, okay, we see aurora around both the North and South Pole. But what is actually causing all of this? It's kind of in two factors. Part of it is the Earth, but the biggest part is actually our sun. So if we take a close-up look at our sun here, we will see that our sun is a giant ball of hot gas, mostly hydrogen and helium. But as we look at the visible surface of the sun, again, not actually a solid surface, but just where we see the light being emitted from, you can see that there are places where we see kind of streams of gas. Let me pause it right here. Streams of gas kind of coming off the visible surface of the sun. That steady stream of gas coming off the sun is what we call the solar wind. And it's gas and charged particles that's just flying out away from the sun. And this happens all the time. Now, you can see in some areas there are places where we have a lot of stuff coming out, other areas where we don't have quite as much, and that does vary depending on what the sun's going through in that moment. So at any given time, how much stuff we have streaming past us in the solar wind is going to depend. But that does mean at all times we have this steady stream of charged particles just blowing off the sun towards us. And we will finish this real quick. Now, in addition to the solar wind, our steady stream of charged particles, we also have activity on the sun like solar flares. So a solar flare, like you're seeing here on the left, and it will loop and play again. There's also a little bit going on up here. A solar flare is when we have a loop of gas, which is called a prominence, and it stretches too far and it snaps. Kind of like when you stretch a rubber band too far. And when that prominence snaps, it flings all of that gas that was in it out into space. And so with a solar flare, you get even more stuff flung out, sometimes towards the Earth. And then at the most extreme, we also have things like coronal mass ejections, where you have just a ton of stuff, even more than flares. But what we're seeing here is a kind of depiction of these charged particles, the solar wind, solar flares, CMEs, whatever, all being flung out of the sun, out into space, and some of it is heading straight for the Earth. Now, that sounds really scary, but for the most part, we are protected. As you can see here, oops, let's pause. You can see that the charged particles, the solar wind, is kind of being deflected around the Earth and not just crashing into it. That's because the Earth has a magnetic field, very much like, a bar magnet, except planet-sized. And this magnetic field acts like a shield. It deflects those charged particles, deflects the solar wind out and around the Earth. So let's turn on our magnetic field here, and we can take a look at it a little bit more. And so you can see that magnetic field coming out of the Earth. The tail end is being swept back by that stream of charged particles coming from the sun. But you see that we have kind of two origin points, right? One near the north and one near the South Pole. Well, I said for the most part we're okay, because not every single charged particle coming from the sun gets deflected by our magnetic field. Some of them get trapped in the magnetic field. And when that happens, those charged particles spiral down the magnetic field until, why didn't my laser pointer just go out? That's not a good time for this. Come on now. They travel down where they will then hit the Earth, the atmosphere of the Earth. I'll use this one. It's super bright, but we'll use this laser pointer. So they travel down until they hit. And because the magnetic field comes from around the North and the South Pole, that's where the stuff gets funneled in. It gets funneled into either the North or the South. And so you have these charged particles hitting the atmosphere around the North Pole and the South Pole. And when they hit the atmosphere, they cause the gases in our atmosphere to glow. And that is what we see as the aurora. It's these glowing gases that have been hit by these charged particles. So that's why we see the auroral rings around the North and the South, because that's where the stuff is getting funneled down. And it's getting funneled down not exactly at the North and South Pole, which is why those rings are slightly offset from that. A little bit louder? So we can see them in Minnesota sometimes. So if we take a look back at the auroral ring, that's such a difficult phrase to say. Remember I said that we get different amounts of stuff coming off the sun, different amounts from the solar wind. We sometimes have solar flares, CMEs. When we have a lot more stuff being flung at us, that means more stuff funnels down and hits the atmosphere. And that can actually cause the auroral ring to grow. And it's during those very active times when that ring grows bigger that it dips down into Minnesota so that we can see it from here. That's why we don't see it all the time from here. But during those really active times when that ring has been pushed back, pushed down, that's when we get to see it really well. Now, if you think about the aurora, the color that probably comes to mind is green. But there are a few other colors that are common. You do also get reds and blues, and sometimes purples, which is a mix of red and blue. And these colors are really just from the gases. Different gases are going to glow as different colors. Think of like a neon light. You have different neon signs that glow in different colors. That's from different gases in those neon tubes, neon light tubes. Why they're not all neon. So the reds and the greens come from oxygen in our atmosphere. And then the blues come from nitrogen in our atmosphere. So depending on which gases are being hit and excited, that's going to cause them to glow and we'll get the different colors. And sometimes we can see these different colors easily from Earth. Like here you can see you've got kind of the tops are red and the bottom of the curtain is green. And then where they kind of mix, you get a little bit more of a yellow or a yellow-white, where you just have red and green mixed together. Blues tend to be much harder to see, just because that reaction is a little bit harder to make those nitrogen gases glow. So green and reds are your predominant colors that you're going to see. Okay, so we now have a pretty good idea of how this aurora, these northern lights, are formed, where the colors come from, why we can sometimes see them from here, but other times can't. Before we get into the last part, our tips and tricks for seeing the aurora yourself, I wanted to explore other planets. Do you think there are other planets that have aurora? Yeah? Well, let's take a look. Let's hop over to Jupiter and take a look there. Would you look at that? Just like Earth, Jupiter also has auroras around the North and around the south. Now you will notice that they are more of a blue color. That's because it's a slightly more energetic collisions going on, but it is caused from the same things. Jupiter has a magnetic field, and it's funneling those charged particles down to Jupiter's atmosphere where they hit and cause the atmosphere to glow. And one more stop, if we head over to Saturn, we see that it also has aurora around the north, and we'll see it around the south as well. Again, caused by the exact same thing as Earth's and as Jupiter's, but we have slightly different colors because we have slightly different reactions going on. And so Saturns tend to be more red in color. All right, let's head back to Earth. These aren't the only two other planets that have aurora. They're just the only two that have aurora caused by the same mechanism. We do see aurora around Uranus and Neptune, but it's really weird because their magnetic field is really weird. And we do also see it on Mars and Venus, which is weird because they don't have a magnetic field. So we don't know how those are formed. So yeah, the best analogs to Earth are going to be Jupiter and Saturn. They have aurora very similar to ours here. All right, so for our last part here, let's talk about how you can see the aurora yourself. Now, there is a common misconception that auroras predominantly happen during the winter, and that's just not true. I think some of this is due to the fact that when you see a lot of pictures of aurora, you tend to see snow-covered landscapes. And that's more so because the regions of the Earth that see the aurora most frequently tend to have snow on the ground for a long period of time. But you can see the aurora any time in the year. It does not have to be winter. An advantage to winter is we have longer nights. So you just have darkness for longer to be able to see them. But you can see them any time of the year. Predicting when we're going to have good aurora here is a little tricky because being able to predict what the sun is going to do is very difficult and very tricky to do. The good news is if the sun does let off something like a solar flare, the light will get to us about a day and a half before the charged particles. So we have about a day and a half warning that the aurora might be more intense once that stuff gets to us. So oftentimes, if you're looking at predictions, you're not going to see predictions for more than a day or so in advance. You might find some places that claim they can predict out to a week in advance, and that's just not true. You can't do that. At least not with any reliable certainty or anything. So, my best advice, if you are wanting to see the aurora for yourself, is to find either an app or a website that you understand and that you can go and look at the kind of daily projection, the daily prediction for the aurora. My personal recommendation is a free app on your phone called Aurora. All it's called is just Aurora. Within this app, it uses your GPS, and so it can show you what the auroral ring looks like for where you're at. You can give other locations to see what things look like there. But my personal favorite thing about this app is you can turn on notifications so that you will actually get alerted when the aurora chances are looking good for your location. And it will tell you, hey, your chance of seeing the aurora is getting pretty good. You should go outside. Now, when you're looking at these predictions for auroral activity, oftentimes you'll see something called the KP index. And that's really just a number scale for how active the aurora is, with zeros being very, very quiet and nines being extremely active. So in order to get a good show here in Duluth, you want a KP index of at least 5. That means we're going to get a show with aurora decently high up in the sky and pretty active and bright so that you can easily see it. Now, I know telling you to plan out your aurora watching a day in advance can be difficult. It does make it hard for people to find the time to get out, typically late at night, in order to go and watch the aurora. The good news is we are going to be seeing a lot more of these opportunities in the next year or so. The sun has an 11-year activity cycle, meaning for some parts of that 11-year cycle, it's really active, and then for some parts, it's really quiet. Well, we are ramping up into the active period, the peak of its activity, where we're going to be seeing a lot more solar flares, more CMEs, and that means a lot more stuff slung at us. And that means a lot bigger, brighter, more active aurora displays a lot more frequently. So the peak is expected to happen sometime next year. So over the next about 2 years, we can expect to have some very frequent, very spectacular aurora shows. So if you haven't had a chance to see it or you haven't seen it in a while, you definitely need to keep checking on things over the next couple of years because you're going to get a lot of opportunities to go and see it. Now, a quick note for those who may not have ever seen the aurora and only seen it in images or videos, you may not see as vibrant of colors as you see in images, just because our eyes don't work as well in dim, low light. And the colors just don't get picked up as much by the parts of our eye that do the seeing in dark. And so you can see colors, but they're going to be a lot more muted, a lot more washed out, and it's going to be a lot more kind of grays, gray kind of dancing lights across the sky. I will say, though, that when they are active, you can really see them dancing around, moving like you're seeing on the dome now. It is quite a sight. Now, for those in the Duluth area, there are a few places that you can head out to see the aurora when they're happening. And when they're really active, you don't have to get that far out of town. I know of people who have had success down in Brighton Beach. Hawk Ridge is another really popular spot. When I go out to see them, honestly, I hop on the scenic highway towards Two Harbors, drive down for about 20 minutes, and then pull off of one of those scenic overlooks. It's nice and dark, and you get some beautiful views out there. So to leave you tonight, I want to show you a time-lapse video we have of the big aurora display that we had in March of last year. And this was captured up at the end of the Gunflint with a camera that we have on the Chickawauk Museum. But this was back on the night of March 23rd to March 24th. And it really was a full sky display. This was my first time actually getting out to see them, and it was stunning. It was the entire sky. They were dancing and moving really fast. It was just spectacular. And we can expect displays like this very frequently over the next couple of years. Now, if you're wanting to see more time lapses like this, the feed for the all sky camera, which is what this was taken with, is up on our website. I will go ahead and tell you we're having some slight technical issues with the computer running it. It is, again, up at the end of the gunflint, so getting people out there to maintain it this time of year is difficult and dangerous, but we're working on it. We'll hopefully have that back up and running very, very soon. But in the meantime, you can also, on our website, we have, I can't think of the word. We have all the past time lapses and images and stuff that you can always go and check out. All right, well, that brings us to the end of our show. Hopefully, you now have a good understanding of the aurora borealis, or northern lights, and are ready to go aurora chasing once we have our next big display coming up. I'm going to turn our lights up. Were there any other questions? Say again? Oh, we have lots of telescopes and observatories that just watch the sun. So we see when something like a flare happens. And again, that gives us about a day and a half warning before the stuff from the flare actually gets to us. And so that's where our predictions are coming from. So that's why making these predictions is extremely difficult, because we don't really know what the sun's going to do. We're just kind of watching and then very quickly going, oh, hey, there's something. Expect some good aurora in the next day or two. Yes, we do need clear skies to see it. That is a common problem with all things astronomy. We are at the mercy of the clouds. All right. It does have cloud cover information on it, but it will still, even if you do have cloudy conditions, it will still tell you that the aurora is getting active. That way you still know in case, it starts to clear up or you want to travel somewhere that doesn't have clouds. Yeah. All right. Well, if you have any other questions, feel free to come back and talk to me. Thank you all so much for coming. I hope you enjoyed the show. Before you head out, in front of the TV at the main entrance are some star charts. You're welcome to take those with you to help you navigate the night sky. Again, thank you so much for coming out. Have a safe trip home and a wonderful rest of your week.